In this video, we are talking about the division algorithm. So I want to motivate this by looking at an example which says find the remainder in the following division problems. So part A says 51 is divided by 8. So thinking back to when we used to do division way back when, you might remember that, well, 8, goes into 51 6 times, and that becomes 48. And that's a little bit short. I would have to add 3 to it. And if I add 3 to it, we get 51. I can also think about this visually on a number line, where if I'm dividing by 8, I sort of want to, count in multiples of 8 until I get really close to 51. So I know 8 times 4 is 32, 8 times 5 is 40, 8 times 6 is 48, and now I'm pretty close. And if I go 8 times 7, well, that's 56, and that's too big. So the number we are interested in, 51, is here. And when we calculate the remainder, we find this multiple like this. That's, the closest one to 51 that's still like less than or equal to it. And then we see, well, how far is it from 48 up to the 51? And they're 3 units apart. Okay, all right, let's do another one. What if I did negative 51 divided by 8? So, okay, so if I thought about this again with a number line, now and I want to count multiples of 8 getting down to a negative number. So I know I'd have like negative 40, and then the next one would be negative 48. Okay, and the next one would be negative 56. Oh, and now I found one that's less than or equal to negative 51. My number negative 51 is here. Okay, and the one that I use, these multiples of 8s that I use, is the first one that's less than or equal to my number, which is negative 56. And then I count, well, how many units is it from negative 56 to negative 51? And it's 5 units. So I could write that as an equation like this, as negative 51 would be 8 times negative 7. That gets me to the negative 56. And then my remainder would be, well, I'd have to add 5. So for part A, my remainder is 3. For part B, my remainder is 5. The one thing I want to be careful about for part B is, well, could I have used, instead of negative 56 as my reference point, could I have used the negative 48 instead? Because, I could do 8 times negative 6 to get to negative 48. And then to get to the negative 51, I could instead try to subtract by 3. And if I do that, I do get negative 51. But the issue with this is, when we define remainders more formally, which we're about to do, the remainder is supposed to be greater than or equal to 0. And that's what doesn't work about this. Okay, so I'm going to put a sad face there. So I did actually have to use negative 56 as my reference point for part B. All right, so we are ready to state the key theorem of this video, which is called the division algorithm, which says that if A is an integer and D is a positive integer, and what I'm going to be doing here is thinking about what happens if I divide A by D. Well, when we do that, there exist unique integers Q and R, such that A will be equal to D times Q plus R. So that's the type of thing that we were getting in our equations in these examples. So this number D is whatever I'm dividing by. So in my examples up here, that was the 8. The A is the other number that I want to divide, the 51. Okay, and the R that pops out, that's called the remainder. This number Q that multiplies the D, that was kind of representing how many times did it go in. That's called the quotient. And then finally, the number I divide by is called the divisor. So it turns out that this remainder always is going to be greater than or equal to 0 and less than or equal to D minus 1. Okay, so all right, so that's our division algorithm. And we're seeing it happen in this example. So we're ready for the key definition. We're ready to define what's called a mod. So when we write A mod M, that represents the unique remainder when dividing A by M. So for example, 51 mod 8 means, what's the remainder when I divide 51 by 8? Oh, and we know that's 3 because we got it up here. We know that's 3. And for this next one, what's negative 51 mod 8? Well, that remainder was 5. That remainder is 5. Okay, so this remainder is unique, meaning there's exactly one remainder. And the key thing that makes that possible, that makes it unique, is, as we saw in the examples up here, when we are sort of first finding this multiple to work with that's really close to our number, well, we're going to be picking that multiple that's, the closest one to my number that's less than or equal to it. And that's what ensures that there's going to be just a unique, exactly one remainder. Okay, so this term mod is like the percent symbol in some programming languages. So in programming languages, there's this notion of calculating the remainder, and that's often used in code. And the percent symbol often shows up as a way to represent that. All right, so let's end with an example. So clocks work in mod 12, or sometimes mod 24, because I could either have a 12-hour clock or a 24-hour clock. For example, what would a 12-hour clock display 7 hours after 9? So 7 hours after 9, if I do this using my mod notation, I would be doing 9 is what I'm starting with, adding 7 hours to that. And then I'm going to figure out, well, what is that going to be mod 12? So I write whatever my number is, and then after that I write mod whatever I'm dividing by, in this case 12. Okay, so 9 plus 7 is 16, 16 mod 12. And what that means is, what's the remainder if I divide 16 by 12? Well, I might be able to even just see this in my head. Well, that remainder is going to be 4. That's going to be my remainder. And that's our answer.